Okay. So first of all, remember that exam 1 is on Friday. And the topics are everything up through strain and constitutive relationship. So no principal stresses, and none of the stuff that we're going into today at some point. Anybody have any questions about the test? Okay. Anybody have any homework questions you want me to go over? All right. Well, so we've been, and also before I do that, remember weekly assignment 1 is on D2L. And I think, it's due whenever it says on D2L, but I'm pretty sure it says a week from Wednesday.
The 14th.
Yeah. So due Wednesday, 2/14. Okay, so we've been talking about the relationships between stress and strain, how to get the things that you need for the compliance matrix through a tensile test, how to represent stresses in different coordinate systems. I didn't talk specifically, I don't think, in a lecture about how to find strains in a new coordinate system, but how would you do that? If you need to find if you have the strain in one coordinate system, the Voigt strain, and you want to represent it in another coordinate system, how would you go about doing that?
You just convert to stress.
Exactly. You'd have to use the stiffness matrix, the inverse of the compliance matrix, to go to the stress. Then you'd have to transform the coordinate system for the stress, and then go back to strain again using the compliance matrix. Yes?
So there's no strain tensor.
There is such a thing, but not in this class. The strains that we are using are not tensors. What is a tensor? It's the same thing as the distinction between a vector and just a column matrix. You can make, you can take a bunch of numbers and put them in a column matrix, but that doesn't make it a vector. A vector is something that is invariant. The meaning of it is invariant under changes of coordinate system. So you can think of it as like only vectors have the relationship with rotation matrices that we've sort of talked about a little bit. And tensors are the same thing. You can think of them as bigger multidimensional versions of vectors. For something to be a tensor, it has to have this relationship with rotation matrices. And so our strain, even if we put our strain you could put our strains in a matrix the same way we did with our stresses. But if you then tried to use the rotation matrices to re-express it, you'd get a different meaning thing. And that's why strains, as we see them, are not tensors. You can fix that, but it makes the math more complicated. And this is the interpretation of strains that's more useful in engineering practices. So now what we're going to get into is really what we're going to do for most of this class. And that is, now that we've found all these relationships, We're going to figure out now how to go from a body with loads on it to figuring out what the stresses are at different points in the body. You know, then you can calculate the strains, the principal stresses, all that stuff we've done before. But so far we haven't, like, you have a lump of metal and you apply a force here and a force here. We haven't talked at all about how to figure out the stresses in the material. So now that's what we're going to spend most of our time doing. Okay, so the first thing that we have to talk about is, so now we're getting into the heart of this class. And that's determining the stresses at points in a body from the external loads. Throughout this class, it's not always going to be the case that this is true, but this will often depend on Saint Venant's principle. This thing called Saint Venant's principle. Ooh, this is the other kind of principle. If you want to sound smart when you write stuff to people, you have to get your principle types right. So Saint Venant's principle, Saint Venant is some French guy. And Saint Venant's principle says if you have loads on some body, okay, so let's think about having this bar and loading it with point forces. Okay. How is this body going to deform? You don't have to know anything about the math to know that this is going to deform something like, so say that this is connected by something welded to these 2 points. And basically we're just applying forces, tensile forces at 2 different points. And you know just intuitively that this is going to deform weirdly at those 2 points. Right, I mean, if you're just focusing on 2 almost infinitesimal points to apply this force, you're going to get weird stretching around that point. And that weird stretching at those points is going to cause weird stretching at the points around it and stuff. Okay, how does that compare to, now, what if we had the same bar, but instead of applying point forces like that, we applied uniform distributed loads that came to the same force F on each side. Well, what's this deformation going to do? This is actually just going to stretch perfectly uniformly at every point. There's not going to be any weird stress concentrations near the point where the force is applied. Okay. But the key thing is, Saint Venant's principle says, as long as you don't get too close to those stress, those stress concentrations, as long as you don't get too close to those point forces. So just get rid of this and this. And this and this. And don't worry, don't think about them over here. As long as you don't consider points too close to the loaded face, the stresses will be identical no matter how those loads are applied. No matter how the loads are applied. So no matter how complicated the loading is at the endpoints here, we can treat it like it's this uniformly distributed load where things are simple, okay? All we have to do is not, we have to ignore what our results say close to that loaded face. And so how close is too close? It's going to be about the longest length dimension of the loaded face. So it works perfectly. Like the ideal case for using St. Venant's principle is like what I drew up here, where the loaded face is small, the other dimensions are long compared to the loaded face. Then you can just, like in this case, if this had a size of like a length dimension of 1 inch on the loaded face, just go an inch away from the endpoints, and everything else is going to match really well. Okay. Notice that means you can't use this all the time. So if you have a body like this, we're not going to ever be able to calculate the stresses inside this material because there are no dimensions anywhere, there are no points anywhere that are that dimension away from the loaded face. So since every point is within the longest dimension of the loaded face, there's going to be weird, complicated stresses all through this material, and there's nothing we can do about it. Okay, you can do it with more complicated methods, or you can do it with finite elements, but not with the approaches we're going to use in this class. So in that case, you can't trust our calculations anywhere. you know, and when I say trust our calculations would be assuming that this is loaded like this. Okay. And so now we're going to talk about members. Yes, Alex, question?
Well, I was just trying
Okay. So the first thing we're going to talk about, the simplest case, is members in pure tension or compression. So let's think of, I'll draw it with a round cross section this time. So let's say that we have a force like this. This is a member in pure tension. And if this is the cross-sectional area, so this has an area A, and I'll draw a coordinate system just to be clear about what stress we're calculating. So then the z-axis would be out towards us. The XX normal stress is F over A. And remember that that's ignoring what's happening at the endpoints. Okay, so for example, I mean, this is no different than what we did with the tensile test. So if you have a member and you have a load of 5,000 newtons applied like that, and 5,000 newtons applied like this, and the cross-sectional radius is 1 centimeter. Then the XX stress is going to be, we're going to consider compression negative divided by pi times the radius squared. And you get a value of negative 1.59 times 10 to the 7 pascals. And so the stress tensor, and remember that stresses are valid for a single point, right? So so let me just try to speak carefully about this. What we're calculating is that this is the stress at every point in that member as long as you're away from those two loading points, those two ends. Yes?
Because we're assuming it's a distributed load across the entire surface, it doesn't matter if we're off like the center of axis.
That's right. Yep.
We could be way out at the edge.
Yeah, that's right. Although, I mean, if you're far enough away, I suppose it's going to turn in order to be in static equilibrium, and then you have to worry about the loading angle compared to the beam's angle. You know what I mean? But yes, yes, that's right. The stress tensor then would be negative 1.59 times 10 to the 7, zeros everywhere else. And a stress cube would be 1.59 times 10 to the 7 and nothing anywhere else. So what kind of things have you seen in statics where the members are loaded along one axis in tension or compression?
Rope,
What?
cable.
Oh, yeah, that's true. Yep. That wasn't the one I'm thinking of, but yes, that's right. Cables always are that way, but I was thinking of trusses. Okay, so let's talk about trusses a little bit, just remind you, like the people who took statics from me, we didn't really focus on trusses much. So let's talk about the calculation of trusses and determining stresses and strains in the members of trusses. So trusses have every member in pure tension or compression. Mostly in my class, almost exclusively in my statics class, we talked about a fully general method for calculating structures that produces more equations and more variables, but it works on everything. Okay, so in this class, let's do the truss simplification, at least for now. And okay, so first of all, you have to be able to identify a truss from other structures in order to get any meaningful results. So a structure is a truss if every member is a two-force member. That requires negligible weights for the members. So we're always calling the weight 0 in order to use the truss simplification. Bless you. And it requires that every joint is a pin joint in 2D or a ball and socket joint in 3D. So pin joints would be for a 2D problem. Ball and socket joints would be for a 3D problem. So if a structure meets the truss requirements, treat each member as a cable. So we're going to assume that positive is tension. And then isolate each joint use Newton's second law and calculate the positive, or you can also get a negative tension, which would be this thing is in compression. A cable obviously can't support compression, but a member in a truss can. So calculate the positive or negative, tension. Negative tension is compression. Okay, so let's make a truss and just calculate the stresses in each one of these members at points, any points along each one of the members. So here's the example. Let's say that it's an equilateral triangle. And all the joints are pin joints. And that's a roller in order for it not to be statically indeterminate. 60 degrees, 60 degrees, and every length is 1 meter. And let's say that there's 1,000 Newton force here. And actually, will you go back up to your notes? Sorry about this. When I described a truss, there's one more thing that that has to be true. So it requires negligible weights, pin joints and ball and socket joints, and it requires that external loads are only applied at the joints. For more facts about trusses, you can go to your local library. More information about the fascinating world of trusses. So we're going to calculate the stresses, and you can think of it as like the stress tensor for points in each member. Okay, I'm going to label these joints. I'll call this A, B, and C. And I'm going to label the members. I'll call this one 1, 2, and 3. Okay. And so I'm just going to go through the joints one by one until I have enough equations to solve this system. So first I'll start with joint A. and we're treating this like it's a particle. There's this tension from member 1, I'll call that F1. There's a tension from member 2. And then the truss is connected to the ground by a pin joint. So we don't know the direction of that force. So I'm going to put that in as an unknown force vector, and I'll just call that the reaction at A. Okay. And because of the 60-degree angle, so if I go to Newton's second law, I have F1 times cosine of 60, F1 times sine of 60, and then I have F2 0, and then plus RA x and y components. So this gives me my first two equations. So I have, the first equation is 0.5 F1 plus F2 plus RAX is equal to 0. And the second equation says 0.866 F1 plus 0 plus RAY is equal to 0. That's two equations for four variables. So we can't do anything with that yet. We just have to hang on to these and we'll solve it as a system at the end. Anybody have any questions about the setup for this first one? Then we'll go to joint B. So this one, remember we're thinking these, yeah, question?
Can I get a better look at the joint A?
Yeah. Yeah.
Thanks.
Sure. Okay, now joint B, what's going on there? So there's the tension from member 1, the tension from member 3, and then there's the 1,000 Newton force. So we have F1 going this way, F3 this way, and 1,000. So Newton's second law says this is just in the opposite direction of the other one we had. So you can think of this as negative F1 times the cosine of 60, negative F1 times the sine of 60. This one is negative 60 degrees. So I'll write this as F3 times cosine of negative 60 F3 times the sine of negative 60 plus 1,000 0 is equal to zeros. And so we get two more equations. Equation 3 says negative 0.5 F1 plus positive 0.5 F3 is equal to negative 1,000. And equation 4 says negative 0.866 F1 minus 0.866 F3 is equal to 0. By themselves, we could solve these two for F1 and F3, but let's just roll through, get all the equations, and then solve it as a system at the end. Okay, so what do we have now? We have 4 equations. We added one more variable, so we have 5 variables. And now we'll go to joint C. We have the tension from member 2 and the tension from member 3. And then we have the roller that's going to apply upward force, perpendicular to that surface on this member. So I'll call this RC, but we know the direction of that one because it's a roller. And so Newton's second law says negative F2, 0. Plus F3 times the cosine of 120 degrees, F3 times the sine of 120 degrees, plus 0 RC is equal to zeros. So our fifth equation says negative F2 minus 0.5 F3 is equal to 0. And our sixth equation says 0.866 F3 plus RC is equal to 0. And so now we have 6 equations for 6 variables, and we can solve this whole system. Okay, how do you want to solve 6 equations for 6 variables? Substitution? Yeah, let's use a matrix. We're going to use reduced row echelon form. All of your calculators do this. So we'll make an augmented matrix that has 6 rows and 6 plus 1 columns. And I'm going to put these in here as F1, F2, F3, RAX, RAY, and RC. And then the last one is for the constants. And now the rows are the 6 equations. What?
If it's like that.
Yeah, this is statics. So, okay, and then we're going to go through the 6 equations one by one and just write down the coefficients of all of these variables. Remember that, I mean, I already did it when I put these equations together, but remember you have to get the constants alone on their side of the equation. Okay, so equation 1, F1s, we have 0.5 of them. F2, we have 1. RAX, we have 1. And everything else is zeros. Equation 2, F1s, we have 0.866. And RAY, we have 1. And everything else is zeros. Equation 3, F1s, we have negative 0.5. F3, we have positive 0.5. And this time we have a constant of negative 1,000. If you ever set up this augmented matrix with all zeros in your constants, you're just going to get zeros for all your answers. So probably something went wrong in setting up your equations. Equation 4, F1s, we have negative 0.866. F3, we have negative 0.866. Everything else is zeros. And then for equation 5, F2s, we have negative 1. F3s, we have negative 0.5. And equation 6, F3s, we have 0.866. RC, we have 1. And if you enter this matrix into your calculator, you know, store this as whatever, A. And then run RREF of that matrix. What you'll get out is another matrix of that same size. And it's going to be, so the first 6 by 6 of this matrix is just going to be ones on the main diagonal and then zeros. The only thing you need to get from that is that it worked. And then it's going to give you, that last column is going to be the answers in the order that you entered your variables. Did anyone do this yet?
Yeah.
Okay. Someone read them to me and then let me know if you get different answers.
Well, I'm not showing my answers.
Okay. Say them at once. 1, 2, 3. Yeah, right.
F1 was 1,000. Yeah, I got it.
1,000? Okay, hold on. Oh no, wait, bad timing. I thought you were going to say when my computer froze. Yeah, right. Okay. 1,000 is F1. Negative 500?
Just 500.
500 for F2. So far, so good.
Negative 1,000.
Okay.
And negative 1,000 again. Negative 866. And 866. Oh, I didn't mess up.
Yay. Okay, well, those, for our purposes, we don't care about those reaction loads. We only care about the tensions, the plus or minus tensions of the members. Oh, and remember when I said this? You might not have written it down. That's your mistake, but the cross-sectional areas of each of these members are, let's see, 0.001 meters squared. I just knew I could see some people not writing it, so I thought I'd mention it again. Okay, so now that we have these, for member 1, so now we use the coordinate system to do these calculations, right? But now you can forget about that coordinate system and think about a coordinate system with the x-axis along the member. So, you know, you can think of it as like member 1 is in tension. With the x-axis like this. You know what I mean? This coordinate system I drew here in red does not correspond to the coordinate system we used for the statics, but that's okay. And so sigma xx is equal to positive 1,000 divided by 0.001, and that is 1.0 times 10 to the 6 pascals. And so the stress tensor for that material is 1.0 times 10 to the 6, zeros everywhere else. And now that you have that, you could calculate the strains and everything. Okay. Member 2. This was in tension of 500, right? Before I write that down, remember that, so what points is this, what points is this stress tensor valid for? Any points that are not right at the ends. So don't trust your answers there, but everywhere else in here, this is the stress tensor. Okay, because of St. Venant's principle. For this one, again, ignore the ends. But the stress is 500 divided by 0.001. And so the stress tensor for points away from the ends is 5.0 times 10 to the 5th, 0, 0, and then for member 3, this one is in compression of 1,000 newtons. So the the XX stress is negative 1,000 divided by 0.001. So that's negative 1.0 times 10 to the 6 pascals. And so the stress tensor for member 3 is negative 1.0 times 10 to the 6, 0, 0. Okay, one thing about these uniaxial loading problems, where everything's just in pure tension or pure compression, is the stress tensor that you get out of it. Notice that that's already a principal stress tensor. Okay, so if a question asks you to calculate the to calculate the maximum shear stress. How would you calculate the maximum shear stress for this? Normally, you would calculate the eigenvalues to get the principal stress. But what would the eigenvalues tell you? Yeah, it would tell you, it would give you the three answers, 0, 0, and -1 times 10 to the 6. And then you'd be like, stupid, stupid, stupid. You know, so.
And then the maximum strain would be just half of this?
Half of that, exactly. And since that's an absolute value, not the maximum strain, remember, it's the maximum shear stress. But yeah, the maximum shear stress absolute value would be 0 minus negative this, so it would be, 5 times 10 to the 5.
Why would it be half of it?
Because remember that the formula is the maximum minus the minimum divided by 2. And our maximum in this case is 0. Our minimum is -1 times 10 to the 6. Okay, so I think what you're doing is just some truss things where you go through these steps and then probably calculate strains at the end. Okay, that's all.
What are the trusses?
What?
I want into trusses.
You already should have done it up.
Just to make trusses fun, just think of how happy you are that you're not